Alright, let's talk about computers. Your phone, your laptop, they all run on tiny little switches. We call these switches bits. A bit can be either a 0 or a 1. It's like a light switch. It's either on or it's off. Simple, right? To make these switches do useful things, like adding numbers or showing a cat video, we use something called a logic gate. A classical logic gate, like an AND gate or a NOT gate, takes in these simple zeros and ones and spits out a predictable 0 or 1. A NOT gate, for instance, just flips the switch. If you put a 1 in, you get a 0 out. If you put a 0 in, you get a 1 out. It's a fundamental building block of all the digital technology we use every single day. Now let's dive into the quantum world. It's a place where the rules get a little strange. Instead of bits, quantum computers use qubits. A qubit is a quantum bit. And here's the cool part. A qubit doesn't have to be just a 0 or a 1. It can be a 0, a 1, or a mind-bending combination of both at the same time. This both-at-once state is called superposition. Think of it like a spinning coin. While it's in the air, it's not heads and it's not tails. It's a mix of both possibilities. It only settles on one when you measure it. Qubits are like that spinning coin, holding more information than a simple on or off bit ever could. So if we have these superpowered qubits, how do we control them? We use quantum gates. A quantum gate is an operation that acts on a qubit, changing its state. Just like a classical gate flips a bit, a quantum gate can manipulate a qubit. But because qubits are so much more complex, quantum gates can do much more amazing things. They can nudge the qubit's state, rotate its probabilities, or gently guide it from being mostly a 0 to being a perfect mix of 0 and 1. They are the tools we use to perform calculations in the quantum realm, the tiny little engines that drive a quantum computer forward. The big difference here is possibility. A classical gate takes a definite state like 0 and gives you another definite state like 1. It's a one-to-one swap. A quantum gate, however, takes a qubit that might be in a state of superposition and transforms it into a new state of superposition. It works on the probabilities. For example, it could take a qubit that is 100% a 0, and with one operation, turn it into a state that has a 50% chance of being 0 and a 50% chance of being 1. This ability to work with a whole spectrum of possibilities at once is what makes quantum gates, and quantum computers, so incredibly powerful. Let's meet some of the most important players on the quantum gate team. First up is the Hadamard gate, or H-gate for short. This is the superstar of superposition. The Hadamard gate is what you use when you want to take a qubit that is firmly a 0 or a 1 and put it into a perfect 50-50 mix of both. It's the ultimate maybe machine. If you send a qubit in the 0 state through an H-gate, it comes out in a state of perfect superposition. Do it again to that same qubit, and pop. It goes right back to being a 0. It's a reversible, predictable way to create and undo that mysterious quantum fuzziness, which is incredibly useful for setting up quantum calculations. Next, we have the Pauli-X gate. This one is a bit more familiar. The Pauli-X gate is the quantum version of the classical NOT gate. It flips a qubit state. If you have a qubit that is a 0, the Pauli-X gate will flip it to a 1. If it's a 1, it flips it back to a 0. It's a quantum bit flip. But because it's a quantum gate, it does this in a special, reversible way. You can think of it like rotating the qubit state 180 degrees around an imaginary axis. It's a simple, reliable tool, but it's absolutely essential for many quantum algorithms. It's the trusty screwdriver in the quantum mechanics toolkit. Now for the gate that really shows off the weirdness of quantum mechanics, the CNOT gate. CNOT stands for controlled NOT. This gate needs two qubits to work, a control qubit and a target qubit. Here's how it works. The CNOT gate looks at the control qubit. If the control qubit is a 0, the gate does absolutely nothing to the target qubit. But if the control qubit is a 1, the CNOT gate applies a Pauli-X gate to the target qubit. It flips it. This might sound simple, but it has a profound consequence. This is how we can create a fantastic property called entanglement. Entanglement is one of the most famous and bizarre ideas in all of science. When two qubits are entangled, their fates are linked, no matter how far apart they are. If you use a CNOT gate on two qubits that are in superposition, you can entangle them. From that moment on, measuring one qubit instantly tells you the state of the other one. If you measure the first and find it's a 1, you know for sure that the second one has also flipped to a 1, even if it's across the galaxy. It's a spooky connection that Einstein called spooky action at a distance, and the CNOT gate is our key to creating it. So how do scientists and engineers actually work with these gates? They use math. Specifically, they use matrices. Now don't worry, it's not as scary as it sounds. A matrix is just a grid of numbers. For quantum gates, we can represent the state of a qubit as a small list of numbers, and we can represent a quantum gate as a small grid of numbers. To apply a gate to a qubit, you just multiply the qubits list by the gates grid. This mathematical operation perfectly describes how the gate rotates the qubit's state from one set of probabilities to another. It's a precise recipe for quantum control. One of the most important rules for these gate matrices is that they must be unitary. A unitary operation is just a fancy way of saying it's reversible. Every single thing a quantum gate does can be undone. If you apply a gate that rotates your qubit in one direction, there's another gate, or the same gate again like with the Hadamard, that can rotate it right back to where it started. This is completely different from classical gates. If an AND gate gives you a 0, you don't know if the inputs were 0, 0, 0, 1, or 1, 0. Information is lost. In quantum computing, information is never lost in a gate operation. This reversibility is a core principle of quantum mechanics. This is why quantum logic feels so strange and non-intuitive to us. Our brains are wired for the classical world. We see a light as either on or off, not both. We understand cause and effect in a straightforward line. But quantum gates operate on a level of reality governed by probability and interconnectedness. The idea that a CNOT gate can link two qubits in a way that defies our sense of space and separation is just plain weird. It doesn't fit with our everyday experience, because our everyday experience isn't quantum. We're used to a world of definite answers, not a world of beautiful, complex possibilities. The logic of quantum gates is a logic of potential. It's about manipulating what a qubit could be when we finally look at it, while a classical program marches forward step by step with definite answers. A quantum program explores a vast landscape of many possible answers all at once. It's like instead of walking through a maze one path at a time, you could send a wave of yourself down every path simultaneously to find the exit. This ability to explore a huge number of possibilities in parallel is the source of the incredible power that quantum computers promise. It's a different way of thinking, a different way of computing. So why does all this matter? Why are scientists and engineers working so hard to build machines based on these peculiar gates? Because the problems these gates can solve are some of the biggest challenges we face. For example, discovering new medicines and materials involves understanding how molecules behave. Molecules are quantum systems. Simulating them on a classical computer is incredibly difficult. But for a quantum computer using quantum gates, it's a natural fit. We could design revolutionary new drugs, create better batteries, or develop materials for more efficient solar panels by simulating them accurately, qubit by qubit. Consider the field of cryptography, the science of keeping information secure. The methods we use to protect our bank accounts, emails, and government secrets rely on mathematical problems that are too hard for even the biggest classical supercomputers to solve. But for a quantum computer armed with the right quantum gates and algorithms, some of these problems become surprisingly easy. This is both a threat and an opportunity. While quantum computers could break our current security, they also give us the tools, through quantum principles, to create new, unbreakable forms of encryption for a more secure future. Quantum gates are also the key to breakthroughs in optimization and artificial intelligence. Imagine trying to find the best route for a global shipping company with thousands of trucks and packages. The number of possible combinations is astronomical. A quantum computer, by exploring many possibilities at once, could find the optimal solution much faster, saving enormous amounts of time and energy. In AI, quantum gates could help us train more powerful machine learning models, leading to smarter systems that can solve complex problems in science, finance, and logistics. The possibilities are truly transformative. In the end, quantum gates are more than just clever tricks. They are the fundamental building blocks of a completely new kind of technology. They are the letters in the alphabet of quantum computation. By learning how to combine these gates, the Hadamard, the Pauli-X, the CNOT, and many others, we are learning to write programs that speak the language of the universe itself. The journey is just beginning, and it's filled with challenges. But by mastering these strange and powerful tools, we are not just building faster computers. We are opening up a new era of discovery and innovation that will reshape our world in ways we can only begin to imagine.